Okay, this is your rectilinear motion part number 3, and we will get into acceleration. So acceleration is another key concept in motion, and you need to understand what this is about. So we're looking at, again, instead of the rate of change of position like in velocity, we're going to look at the rate of change of velocity, yeah, and that is your acceleration. So it's the rate at which your velocity changes, and we're going to look at with respect to time. Okay, so in simple terms, it's going to tell us how quickly, yeah, an object speeds up, yeah, or slows down, okay, or changes direction, yeah. So it's going that direction, now it's going this direction. And so if your velocity stays the same, okay, over time, meaning you've got a constant velocity, yeah, your acceleration, yeah, is going to be 0, yeah, same as your instantaneous velocity, okay, is 0 if your slope, okay, is the same, yeah, if the slope for your position, yeah, when we draw the tangent line, remember, in the velocity section. So same as that, yeah. If your velocity stays the same over time, then your acceleration is completely 0, yeah. A for acceleration, because there's no change happening if your velocity is the same, no change, so therefore no acceleration. Acceleration, you got it only when your velocity go up or down, yeah. So think about, like, a car is moving at a speed of let's say this is your car, and then it's going with a 60, yeah, miles per hour. And so if that's 60 miles per hour and the car still going with 60 miles per hour, yeah, after traveling about, let's say, 30, yeah, 30 miles, you're going with a 60 miles per hour rate, the rate doesn't change, so therefore your acceleration is 0, yeah, there's no acceleration. But if the car start to speed up, yeah, and now the car is going to travel 100 miles per hour. It was traveling initially 60 miles per hour, and now it is traveling 100 miles per hour. So you have a change in velocity. At that time, you're going to have acceleration. Yeah. So the car is now experiencing acceleration. Okay. It's, the feeling, yeah, you can feel acceleration, you can feel velocity, by the way, if you want to understand these results of your motion, yeah, you can physically feel it. So you can take your car and drive, speed up, yeah, speed on, and then go with the same speed, and you can feel the acceleration. Okay, it's going to get affected, the motion will get affected. You will get affected by the motion, okay, and the aspects of motions are your velocity, your acceleration, your momentum as well, yeah. You can be able to feel these we don't have a lot of, like, even if velocity or acceleration, when we describe outside, we use a common word like you can feel the force and things like that, but actually you're experiencing, your car, and if you are inside of the car, then you're experiencing acceleration when you speed up from 60 to 100, okay, 60 to 80 or 60 to 70, and then you slow down, 60 to 40, 60 to 30, 25, it depends on where you're driving in the town, and you can feel the deceleration, yeah, in your physical body. All right, So acceleration is like, you know, like a next step after velocity, I would say, and it's going to tell how your motion is changing. Yeah. So we built up from position and then velocity, and now we're at acceleration. Position change over time going to give you velocity. Velocity change over time, it's going to give you acceleration. Okay. All right, the next problem is your conceptual example 2.1-5. Yeah, so I'm just gonna cut time to give you, yes, the answers here. So at the same time, of course, I'm going to go ahead and explain that for you. So you're driving a car on a city street. Okay, so your first fill in the blank is that the acceleration of your car is blank when you start moving, yeah, after being stopped at a red light. So first your car's right here and you're at stop, yeah, because you're at the red light, and then you're gonna move, yeah, after the red light. So when you think about the acceleration, yeah, it's got to be positive because you have to move from stop, right? So therefore, when you think about how acceleration applies in this example, yeah, um, in this example, we're driving a car on a city street. So when you're stopped at a red light and then you stop moving, then your car's velocity will definitely increase. Yes, so it means that your acceleration is positive because the velocity is changing. Yeah, velocity is changing in your forward direction. Yeah, you have to at least push your pedal to move your car. Yeah, so there you change the position and you change your velocity in a very short amount of time. Yeah, so that's what we're talking about in the very first example. The second one is the acceleration of your car is blank when approaching a yellow light. So now you drove and then you saw a yellow light. So you're going to speed down. Yeah, you're going to speed it down and you're going to stop eventually, of course, because it's yellow. So you're slowing down because of the yellow light. So it means that you're approaching a yellow light and you slows down. Yeah, you slow down. So here the velocity is definitely decreasing. So your acceleration is going to be negative. Okay, it means deceleration. This is acceleration. Now the acceleration of your car is blank when your velocity is constant because you're driving. Yeah, no lights and you keep driving, and you're gonna drive with, let's say, this constant, relatively constant velocity, yeah, which is 30 miles per hour, I would say, yeah, in the city street. So at that time you have no acceleration because you're keeping an average velocity of the same, yeah. And so now you understand acceleration, deceleration, slows down, speeds up, and node speed change. Okay, it's going to be 0. Of course, now we're going to do the same thing as in velocity, introducing new mathematical formula. Right, so here is your equation 1, equation 2 for acceleration. Acceleration, you already know, is the time rate of change of velocity. So let's break it down a little further, and your formula again, AVE for average acceleration, is your change in velocity over change in time. I'm going to go a little faster, yeah? So now you're familiar with the symbols. So this is going to tell you how much your velocity changes over a period of time. For example, if you have a car, yeah, and your car's velocity increases from, like, say 0 to 20, yeah, miles per hour, and that happens in 10 minutes, yeah. So this is your rate, miles per hour. So therefore this is already a velocity, and that is happening, okay, over, let's say, 10 seconds. Okay, so this whole thing is telling you acceleration, yeah. So remember you have time here and you have another time factor there, and you have two time factor. This time factor is gauging you for your position, so your result is velocity. This time factor is we are looking at the velocity over time. Yeah, so you've got your acceleration. So the average, right, acceleration, if you calculate it, you're going to cancel the zero out. So therefore you're going to get 2, yeah, meter per second square. But this is hour, this is second, so therefore your time is double. So therefore, not double, I mean square. So meter per second square. Yeah. So that's your acceleration unit. Okay, your unit. So anyway, so instantaneous acceleration, the same thing, tiny little bitty bit of change. So delta v divided by delta t, and that's your derivative. Yeah. So this is going to tell you acceleration at a, again, specific moment in time, instantaneous. Yeah. So it's like asking how fast the velocity, is changing right now. Yeah, I said right now. So right now, how fast the velocity is changing is your instantaneous acceleration. Okay, and of course that's your derivative. When you have a derivative and you do operation, we call it differentiation. The differentiation symbol, so formula looks like this. Yeah, d and then square s divided by dt squared, meaning we're changing this little velocity, and we're going to write that into the form of position. Okay, so if you write it in velocity, is dot v dot s is going to be acceleration. That's acceleration. This is another symbol, descriptive or symbol for acceleration, because we're putting your v is don't forget, your v in velocity is this, ds, delta s divided by delta t. Okay, so we're putting this whole thing, okay, into here. Yeah, so therefore when you put it, you get d, and then you have d, and then s, so d squared s, and then you have d, and then t, yeah, and you're gonna put that down here, yeah. So you're gonna have 2 of dt, yes. So you will see that, and that's what we're writing, yeah. This actually is like this, by the way. Okay, like that, but we abbreviated it. Yeah, mathematically correct way of writing is dt the whole square, but of course we wrote it this way, very familiar, but we understand that it means there's a hidden blanket in there, yeah, bracket in there, not blanket, I mean hidden bracket in there, yeah. So d squared s divided by dt squared, and if you write it in a dot symbol is dot s, and double dot s, and this is dot, okay, v, and these are all your acceleration formula, how to get it. Okay, okay, if we use the mathematic terms, your velocity is the first derivative, yeah, derivative of position. This means velocity is the first derivative of position, and your acceleration, yeah, directly describe how your position changes over time at an increasing or decreasing rate, yeah. So this is a change of velocity, this is change of position as well. You can define acceleration that way. Okay, second position is your second derivative, yeah, second meaning 2 times. So that's the first derivative of position is velocity, acceleration is the second derivative of position. Okay, and this is your first derivative of position, your velocity, and we're going to put that in there, so you get second derivative of position as your acceleration. I hope you see it. Yes, make sure you see them. Okay, so these equations are connected, okay, because this means that your acceleration directly describes how position changes over time at an increasing or decreasing rate, and you can use these equations because they're all connected, okay, all of them. And your acceleration is going to tell you how velocity is changing, and your velocity is going to tell you how position is changing. Yeah, I'm repeating again and again, so you have to, your duty is to be able to connect them. Yeah, I have photographic memories, so it's so easy for me, like everything is right in there in my head just like that. But for those who can't remember the diagram in the head like a picture, you've got to train your brain to be able to see the progression, like position to velocity, and then velocity to acceleration, and then backwards acceleration to velocity, and velocity back to position, even though it's complex. Okay, so does this make sense? Yeah, or do we want to go into an example? Yeah, so I'll show you, definitely give you more examples. One moment. Of course, we're gonna study with the slope. Yeah, slope again for our instantaneous acceleration. Yes, so we have the acceleration at a given time, and then we're gonna draw, okay, slope, tangent. Yeah, slope of that tangent line. We draw the tangent line at the slope here and here. And you pay attention to what graph you're dealing with. You're dealing with a velocity and time graph. Yeah. And again, don't forget your velocity. You can write it mathematics position as a function of time that way too. Okay. So now we're writing v. Your first tangent, your second tangent, your first slope here, and then your second slope right there. Instantaneous acceleration at that point, at this time. Instantaneous acceleration 2 at this point, at that time. And you have to connect your acceleration to this graph, right? You should be able to do that because we have already done it with position. So the graph here is going to show you velocity. And again, don't forget how to say this graph. So velocity versus time. Y versus X always, yeah? So velocity versus time. So if you want to find a position, at this position for acceleration at that time, we're going to look at that slope, okay? You can see the slope if you draw a tangent line at that point, okay? And at T1, your tangent line has a positive slope, yeah? We can see this little geometric triangle, so you know that that's a positive slope going up. It means that your acceleration a1 is positive, yeah? It shows that this velocity is increasing at that point. Another slope here, point is, here, and this is at T2, yeah? So this tangent line has a negative because of this little triangle, and we can see it's going down. So it is a negative acceleration, meaning it is decelerating at that point. Okay, so it's going to tell you your velocity at that point is decreasing. It means, in other words, common word is slowing down, yeah? So the slope of the tangent, now we know, we have seen this, yeah, 2 times. This is the second time you're seeing. So the slope of that tangent line is going to give you the instantaneous acceleration at this point, okay? So steeper slope means larger acceleration, and the sign of the slope, okay, positive or negative, it's going to tell you whether your velocity is increasing or decreasing. Okay, positive for increasing velocity and negative for decreasing velocity. All right, steeper slope, larger acceleration. Yeah, shallower slope, smaller acceleration. Okay, so does everyone see how acceleration relates to the slope? Yeah, here. So if you have questions, always ask me. Okay, so now we're on conceptual example 2.16, and I'm going to go ahead and explain that to you. So here you have 5 balls, and you're going to throw, they are thrown up. Yeah, you're going to throw them up in the air from the same level with the initial velocity indicated in this diagram. So you have 7 ounces a ball, 30 miles per hour. You're gonna throw it up. B, 40 miles per hour, 5 ounces, 6 ounces, 20 miles per hour. 8, pay attention to the weight of that ball. Okay, so 8 ounces, 28 miles per hour. 9 ounces, ball is going to be 35 miles per hour. So every time you look at it in your brain, you gotta have like, you're going with 9, 8, 7, 6, and 5. Yeah, so meaning the ball is bigger. Yeah, like that. And then of course you can list it up. Yeah, so if you go like 9, 35, 20, 30, yeah, and then 20 again, and then this is 40. Okay, small. So anyway, so that's how you look at your initial data. Yeah, so how high will each ball go relative to each other? So we need to compare because it's relative to each other. So the height of a ball reaches depends on this initial velocity. Okay, because in order for the ball to go up, you gotta put energy in your hand and throw it up. Yeah, so your energy is going to transfer into this ball, so the ball is going to take your energy and then it's going to move up in the air from your hand. Yeah, and anyway, so that's what you're doing. And so with that energy, it's going to go up, and with that energy, it's going to initialize with a particular velocity. Yeah, so you also have a gravity, don't forget it. So when you throw an object upward, your gravity is going to pull it down. Yeah, and it has attractive force on that ball. So it's going to go up, the ball is going to go up in the air like that, but still your gravity is still pulling it down. So it would definitely slow you down. At one point, the gravity is going to overcome that motion, because as this ball goes up, it's losing its energy that it got from your hand. Yeah, because of this, because it's got to use that energy against that gravity, because the gravity is taking some energy out of that ball, so it cannot use up the energy it got from your hand, all of it. Okay, because all of it to take the height, okay, in the air, it's gonna span it against that to compensate that gravity force. Yeah, so these are what's going on in physics. Okay, so when you throw an object upward, gravity slows it down until it stops momentarily at its highest point. Your highest point is telling you, hey, I don't have any more energy to go because I already spent it to take the height against that gravity. Yeah, so the formula that connects, right, the height, so which is this distance it went into the air, yeah, to the initial velocity, yeah, is going to be, they're directly, okay, proportional to the square of that guy. Okay, so the height is going to be directly proportional, meaning like it will go higher if you have more speed. Okay, greater speed. So if you compare, you have 40 and then followed by 35, and then we have 30 followed by 220s. Okay, so you're going to have that is going to reach the highest point. Yeah, because it has the largest initial velocity. Yeah, then you're going to have 35, and then followed by 30 and then 20. If I have to write it nicely, then this is your rank. Yeah, so that's from highest to lowest, and you can write that down. If you check it, there'll be for T, your E is 35, and then your A is 30, and then your D and C is 20 miles per hour initial velocity. Okay, so you now know how to rank it. So the weight of the balls, okay, here we don't need it, okay, because we got initial velocity. Yeah, VI is there. And of course, your gravity acts on all the objects equally because your gravity is the same force, yeah, and it is subjecting to all of this. So these are all affected by the same gravity, the same, all right, force, regardless of what the mass is. Okay. Again, don't forget we say gravity is you have a core, is the core, okay, the center of the planet. Our planet is a downward force like that, okay, pointing to the center. And of course, because of that, you got acceleration due to gravity. So this is where your weight is going to pull back down here. So anyway, so that this and your mass, your weight of the ball, is your gravity. Okay. Okay, I hope it makes sense. Yeah. All right, the next one is your conceptual example 2.1-7. So the following situations, you have 4 of them. Yeah, so illustrations. I'm going to show you your time-lapse pictures of your rolling balls again, and then the time between each, yeah, successive time-lapse image is equal. Yeah, meaning like from here to here, the times is equal, but of course your ball is going with a different velocity, yeah, in there. So the first thing we have to do is you've got to find out which cases out of A, B, C, D have a positive, negative, and 0 acceleration. I'm just going to go ahead and reveal and explain that to you, okay? So in this example, what you're trying to do is to find out, okay, which case has a positive, negative, and 0 acceleration. Sorry, I went to drink some water. So positive acceleration, you need to know, yeah, positive acceleration meaning that your velocity is increasing, yeah, in the direction of your motion. So your motion directions are indicated by this blue arrow. So you gotta find in that direction which one is increasing, which velocity is increasing. Okay, negative direction. Okay, negative no, I shouldn't say direction, sorry. So negative acceleration here that we're trying to find is your velocity is decreasing, okay, meaning slowing down. 0 meaning your velocity stays constant, there's no speed up or slowing down, yeah. So that's pretty easy when you look at this situation. We have already done it with velocity, yeah, in previous problems in velocity section. So when you look at your A and D, see that? Your A and then your D. So the balls are evenly spaced. Again, yeah, you gotta do this thing again, yeah. Now I don't need to do this again. So, but you can see like how the intervals, yeah, time interval changes, but then the spacing is, they're evenly spaced, okay? Meaning like your velocity is constant, yeah? So when your velocity is constant, your acceleration is 0, yeah? So therefore we put that in there. And your positive acceleration, when you look at it, you have C and D, yeah? So positive acceleration means you are speeding up. So we gotta come up with the direction of your force, which is this way, yeah? So the direction of the motion is showing that way, yeah? So therefore going down, yeah? Your force is right here on this side pushing it. So your slope is going down. So therefore you're gonna have a increasing velocity as it moves down. Yeah? So therefore your C has a positive acceleration. All right, because it is speeding up. The spacing between the ball, when you look at it, see, is started with this little. Now when you look at the space, see how big it is, so meaning like it is speed, okay, speeding up. Here your space start with this because your force is here, your motion direction is going that way, yeah, and ended up with a little tiny spacing here, so meaning it is slowing down, so therefore that's a negative acceleration. Okay, I hope does this breakdown make sense to you? Yeah, I hope it is. Just we are looking at the spacing, yeah, constant spacing, zero acceleration, spacing big, eventually small, speeding down, negative, okay, acceleration, spacing small, ended up with very big spacing, that's means speeding up, so you have positive acceleration. Okay, so that's all you need to study. Alright, so the next one is you have the position of two rolling balls. Okay, ball A and B, they're captured at 0.1 second intervals. Okay, going that way. See this little interval, so that's your 0.1. Altogether here, 1, 2, 3, 4, 5. So you have a bigger unit and a smaller units. Two different types of units, 0.1 and then 1 second. 0.1 and then, yeah, and going gradually up. So the balls are moving towards the right, so your right side is that way, and then your left side is this way. Yeah, going in that direction. Alright, you have 6 positions. You have 6 positions for ball B as well, yeah? And you pay attention, please, to the spacing between them, yeah? Alright, now let's see what is the problem. So the problem is multiple choice questions here, and it's what can be said about the ball's acceleration. So you have to think about what can you say about the ball acceleration. Yeah, so we have the ball A's acceleration is greater than ball B's acceleration. So if you think about the ball A acceleration is greater than ball B's acceleration, when you look at it, look, it's difficult, right, for you to say. Because when you look at it, let's make it bigger. It looks like the spacing's a pretty okay, equal spacing to me, yeah, both in both example. See like how equal spacing they are. So to me, you know, the spacings are, yeah, about the same. So therefore, I think, yeah, I would say, you know, evenly distributed for both of the balls, yeah. So ball A and ball B, you have the evenly distributed spacing. So the graph spacing is going to tell us, like, you know, the velocity for both balls are constant. Yeah, they're going with constant velocity, meaning we don't have acceleration. So therefore this and that is gone. Yeah. So now we have this too. So both accelerations are equal, greater than 0. Yeah. So it can never be greater than 0 because the spacing is the same, evenly distributed in both cases. So therefore the velocities are constant. Therefore your acceleration is 0. Yeah. So the answer is D. Okay. Alright, then we're gonna get into the next sections, and that's your kinematics, yeah? So we're gonna look at the forces behind the rectilinear motion. So solving rectilinear problems, so let's talk about it, because here, you know, we're gonna think about the motion in a straight line because it's rectilinear, yeah? So most of these problems, you can solve them by using these relationships. Okay, these relationships mean equation, mathematics equations. So when you look at the very first one, that's your velocity, of course, and your velocity is the rate, change of position, and we usually mathematically say delta s divided by delta t, little change in position over little change in time, and that is going to tell us how position, all right, changes over time. Then the second one is your acceleration, and that's the rate change of your velocity, and that's your dv divided by dt. It's going to tell you how velocity changes over time. And the third one is your relationship between acceleration, velocity, and the position. Okay, all that you do is put this two, together. So what you do is you're gonna put this, see that ds, and then your dv is here, see that, and all you do is a, okay, divided by v, which is we put them together and cancel that, okay, and you left. If you want me to write it, I can go ahead and write that for you. All you do is this, okay, all that we're looking at the acceleration over velocity, okay, and when we write it, we're gonna put the a is dv by dt, so make sure you do this mathematics calculation or rearrangement of the equation this way, okay, and then of course dv is down here, so your ds is down here, and then your dt is up there, and this dt is going to cancel out, okay, so now you're left with this, so we're going to put that to there, so that's your algebra mathematics, okay, and then you're going to put this to there, so you got, okay, this, right, acceleration, and then ds is equal to velocity dv. Okay, so that's how we got these relationship. So this we call it relationship between acceleration, velocity, and position. Okay, so this is going to connect all three variables when solving problems without directly involving your time, because we're eliminating the time, out of the equation. Okay, so we usually solve problems in the forward direction, like that. Remember the progression, so position, velocity, and then acceleration, meaning you can get acceleration from velocity value, and from velocity, okay, you can get the velocity value from position value. All right, so that's how we solve the problem in the forward direction. You start with position, calculate velocity, and then calculate acceleration. So this is a mathematical approach. It's going to help us break down the motion that we're studying step by step. So we're looking at the motion starting from position of that particle of that motion, and then we look at the velocity of the particle in that motion, and then finally we look at the acceleration of the particle in the same motion. Okay, so we now know how the position changes. You can find the velocity by using this equation. You can find the acceleration by using this equation. So does everyone see how these relationships are interconnected? Okay, these are all, it's the interconnectivity in these dynamics, okay, concepts. right, so when you have to solve the problems in a reverse direction, then there is some challenge in your mathematics equations because calculus uh, comes in. Yeah, of course, in this course I am not going to ask you. Yeah, you don't have to worry about it because if you know theoretically and conceptually, you're okay for your major. All right. So there's no involvement of heavy calculus. Of course, we are in engineering technology, so we can be able to use our programming, yeah, which is computation programs like Python or MATLAB in order to solve these complex equation in a very easy way. Yeah, so you're welcome to use if you want to tackle with the problem solving, but I won't be asking you. You only need to recognize how to solve it. Recognize meaning like, oh, if you need to solve the problems in the reverse direction, then we should use these equations. Okay, at least you gotta know this. But of course, I'm not gonna ask you to calculate by using them. Yeah, but you do need to understand reverse direction is you're getting the acceleration, okay, and then go back to velocity and back to position. Okay, so if you look at the reverse direction problems, then you're going to start with acceleration, walking back all the way to the position. Yeah, so your process is you will be using calculus integration. Yeah, to do that. So your process is going to go acceleration, velocity, and then position. So from acceleration to velocity, you're going to use which is so from acceleration to velocity, you're going to use this. Okay, it's a little bit different, but we can go with your equation. Okay, yes, so your velocity is ds divided by dt, and in the reverse, yeah, we are going to use integration. Time 0 go all the way to time t, and your velocity and dt is equal to this integration again, position 0 go all the way to position s, and then ds. So this is showing you from velocity to position, so from here to here that is going, and use this equation. Yeah, from acceleration to velocity, we're going to use this equation. It's going to tell you how velocity changes over time based on your acceleration. Okay, let's go like dv by dt integration time 0 time t, and you can be able to get integrate. This is, in common words, is just integrating acceleration is gonna give you, okay, velocity. Yeah, so that's what's talking about integrating. Okay, velocity is gonna give you position. Yes. And of course, then we can connect acceleration, velocity, and position directly. Yeah, without the time factor, of course. And you can integrate, okay, this way. And we use this, okay, when time doesn't, okay, appear in the problems, meaning like when you're not given time in your problem, then use this equation. Okay, and the most important thing, okay, let me go back one slide. The most important thing is this. Okay, it means that you should be able to solve, yeah, backwards. Yes, you gotta know how acceleration, velocity, and position are related. Yeah, you can think of an example like a car, decelerates, meaning like speeding down, yeah, slowing down is your negative acceleration. So when you integrate, when the car slows down like that, your acceleration is minus a, yeah. So if you integrate, um, you're gonna find how its velocity decreases. So this is your v decreasing. And you can also determine your position, which is distance it travels before it stops. Okay. Forward, you're gonna do differentiation, yeah, d mean differentiation. Backwards, you're gonna do integration. Okay. Some people like to write only this way, and we usually do differentiation, derivatives, and then we just arrow it out and then write the integration. Okay, integrate a, you'll get v, integrate v, you're gonna get s. Differentiate s, you're gonna get with time, of course. Differentiation is over time. So differentiate s and you get v, differentiate v and you're gonna get a. Okay, so that's how we trying to remember. Because this is your constant acceleration equation, so if you have already taken your physics, yeah, 1, and they use the same equations, okay, for constant acceleration equations, and we can be able to use them, yeah. I'm just gonna review very, very quickly for you. And of course, I'm not going to ask you calculation in this course. So now here, when you look at it, constant, acceleration is a very, very common situation in physics and engineering. So in textbook, we always have a constant, acceleration problems, and you would use one of these equations. Yeah? So position as a function of time, yeah, say position as a function of time. So this equation is going to tell the position, which is your s, yeah, so you can be able to calculate position by using this equation. At time t, you have initial position and then initial velocity that the particle, right, travels, and initial acceleration. Yeah, so all you have to just plug it in. They will give you some variables or values, and then they're going to ask you to calculate one of it, and you use your mathematics algebra to solve it. Okay, velocity as a function of time is this equation. So this one is going to give you how velocity is going to change over time, yeah, starting with the initial velocity v0. You have an initial acceleration, yeah, your initial time and the final time. And the last one is your velocity in position, yeah, relationship. There's no time in here, yeah, no time factor in that. So we have 3 equations. They're very helpful, yeah. And this guy doesn't have time. So when time is not given, it's very easy to calculate, yeah, because it directly relates the velocity to the displacement, yeah. This is displacement, don't forget it. So that's your delta S, yeah. Delta S is final position minus initial position, yeah. So sometimes you're going to see this instead of that, okay. This one is a delta T, that one is also delta T. This is delta t. So that's another way that you can be able to write, yeah. So some textbook is going to trick you. Instead of writing this way, they're going to abbreviate that way, yeah, but it's the same constant acceleration equations anyway. So you can go back to your car, yeah. Car is going to start at rest. So if the car is at rest, your initial velocity is 0. Acceleration, okay, let's just give like 2 meters per second square if it's going. Starting velocity 0, the car is going to accelerate. Yeah, remember the red light problem? You stop your car, yes, at the red light, and then you drive. So when you drive, your car is going to accelerate. Let's say accelerate with 2 miles per, sorry, 2, maybe let's say meter, yeah, 2 meter per second square. So that's your acceleration after the stop, yeah. At the stop, you have velocity is completely 0. You go with an acceleration when you drive out of your red light. So you can use one of these equations, okay? We can find how far it travels after, let's say, 5 seconds, yeah? And how fast it is moving after covering, going a certain distance over time. So anyway, those kind of trouble, you can calculate these problems by using these constant acceleration equation. All right, I think everybody is comfortable with dynamics up to this so far. I try to make it as easy as possible. Yes, you will use this equation, 3 of them, only when your acceleration is constant. Okay, so example 2.2-1. So if I did ask you, I will ask you something like this. Yeah, very simple one that you can plug it in. No calculus, okay? I hope you feel better. If I do ask, I'm going to ask a very, very simple, derivative like this. But I won't ask you to calculate. I will ask you if you can recognize it. Yeah, I will calculate everything for you. Probably I ask you if this answer is true or not, like that. So anyway, so let's see this, and I'm gonna walk through this example for you. So we're given this position, equation, and then we have to find velocity. Yeah. So first, your given equation, is a position function. Of course, we have here t cubed minus 2t plus 5, and then we have to find vt. Yeah. So first, we are going to look at what's going on, and we know your velocity is the time rate of change of position, which is this guy. So velocity equal to ds divided by dt. ds and dt, it means that we are differentiating, so if you see this, you know that we are in differentiation. So we're going to differentiate the position function, with respect to time. When we say function, it means this, we're going to differentiate the position function with respect to time. Basically, if you use a symbol, it's just ds by dt, we're differentiating to get, all right, velocity, because our forward, calculation going like this, yes, is differentiation. We already said that, if you go this way, differentiation, and if you go that way, integration. Okay, so now we're doing this step. And then, of course, we're going to differentiate, we're going to use this. So first we put there, and then when you differentiate it, you're going to recall your mathematics. I don't know, some people have taken or not taken, but I'm just going to go ahead and explain it for you. Differentiate meaning we're going to change this equation, so we're going to put this down. So put 3 down. So we put this 3, and 3 is now here down. 3 minus, 1, because we put 1 time, down. So 3 minus 1 is going to be 2, right? We're going to put that down, and then we're going to take 1 out of what we have for the power, and that is 2. So 3 minus 1 is 2. The first step is you put this down. So we got 3 in front of t. Then you take 1 out from the power. So you got 2. Yeah? And we do the same thing. So copy, that's a minus. You have 1 here. Okay, you put 1 down. So that's 2. And then you're going to take 1 out. If you put 1 down, you take 1 out. So when you take 1 out, t to the power 1 minus 1 is t0. Yeah? t0 is equal to 1. So these are your mathematics. Yeah? t1 minus 1 is equal to t0. And t0 is equal to 1. Yeah? And that is the whole thing after differentiation. You have a hidden 1 here. 2 times 1, 1 is hidden. So that's or. There's nothing to put down, okay? Even though you put this down, there's nothing to differentiate. Yeah, this is just a constant, no t. So therefore that's 0, okay? If you have just a number without the t, there's no need to differentiate. Differentiate means we're putting the power down and take, all right, 1 out of the power. So that's what we do for in differentiation. Put the power down. The power is 1. Yeah, down. 2 times 1 is 2. Take 1 out of the power. Yeah. So when you take 1 out, that's 0. So t to the power 0, your exponents. Yeah, that's 1. No t. So therefore no power to do anything. So therefore a constant regular number is going to be 0. Yeah. So that is differentiation. Okay, so if I do ask you, I will ask you something like that, very, very simple one. Okay, so if you have any questions about how we apply the derivative, yeah, in differentiation operation, then let me know. Okay, all right, now this is backwards. Yeah, example 2.2-1. So you're given actually a velocity. I think that somebody got this, yeah, backwards. So it's supposed to be, let me change it. So I change it, okay? So we're not going backwards. So you have, where is my drawing? Yeah, okay. So you have velocity, yeah? And then you have position. So you have to find position. So now we're going backwards. So if you go backwards, you have to do integration. Yeah. So here is your given equation for velocity. So we're going to use this. So velocity is equal to ds divided by dt, but this time our direction is backwards. Yeah. So first we identify that we know that the position is the integral of your. If we go backwards, we do integration. Yeah. So therefore, my integration sign is so difficult. Anyway, so you're going to integrate velocity to get position. Yeah. So that's what we do here. So we're going to integrate velocity is we usually write this way. Yeah. And I hope you can be able to see that. Yeah, all you have to just put the integration here. So you're gonna get this dt come from that side that way. Okay, and then of course if you integrate, you have to integrate this side. So you're gonna have integration of ds. Yeah, that's how we write it. If you want me to write it in here for you, see, I write integration sign. I take dt to the other side, that's your algebra, and then I add integration to balance that integrations. So you get this, okay? So when you integrate this, it's the reverse of your derivative, yeah? So the very first one is we have to integrate t. So when you integrate t, you're gonna get this, okay? So first, you have a power 1, you're going to increase this time. You're not subtract, but increase. So if you increase 1 to what you have, you got 2. this is where your 2 come from, because that's we're adding 1 to the existing power 1, and you got power 2. Every time you add, you're going to divide it. Yes? So therefore, we're going to divide it with 2. Yes? Alright, so that's your integration of t is t squared by 2. Some people try to memorize. So if you have t, then you're going to get t squared by 2 for integration. So that's my integration is finished. Okay? Then we have to integrate 4. So therefore, your integration is you have 1. I said there's a hidden 1. And you're going to write it in the form of t. And that t is, it will be 0. So the power of 1, if you the power of t is 0, which can equate to the hidden 1, right? Which is multiplying your existing 4. So in order for us to integrate this, okay, which is equal to 1, we're going to add a power, yeah? So that's what I did. So you end up with t. Now t has t to the power 1, okay? So if you add 1, you have to divide with that power. So the total power here is 1. So that's where your t come back in, okay? So that is integration, okay? And we integrate it with respect to t, all right? So this may integrate v with respect to t, meaning the value for v is defined by using t, which is this guy. The value for v is defined by using t. That's what it's saying. And it said, please integrate it, meaning go backwards, please. So we integrated and we got this. This one, we're going to integrate this, yeah? So if you integrate s, if you integrate the derivative, the change of s, yeah? The derivative of s means the little change of s, all you have is s, okay? So this one is another integration problem, and this time you use your, okay, cosine and sine, yeah? Of course, again, I am not going to ask you, right? So don't feel so bad here, all right? I'm just going to go ahead and explain it to you, right, how things work. So anyway, so acceleration is given to you, and we got to find the degree. The first thing you do is a forward or reverse. Since this is reverse, yeah, all you have to do is integrate this, and you're going to get that. So now we're going to change our equation. So your equation is you are in acceleration and velocity, so therefore we're going to use this equation, yeah? So this is acceleration and velocity derivatives equation. We got to go backwards, so you have to integrate. So if you integrate this, you have to integrate that. We're going to bring this to the other side, yeah? So we're doing it faster, yeah? So now you see this? So that's what you're seeing. And then of course, you have time going from 0 to t. Yeah, we start putting the initial and final time right in there. And your a is given to you with this equation, so I'm putting that into here in place of a. On this side, we only have that dv, yeah? And of course, going from 0 all the way to the final velocity right up there. So that's what we quickly write it, yeah? Of course, then you have to integrate this equation. So if you want to integrate cosine, we get sine, okay? Omega, and then t is inside of it. And when you switch cosine to sine, we usually divide it with the, okay, the omega, which is inside of it, right? So why? Because this is your t function, yeah? I'm going a little bit fast, so all you have to just listen to it. And you know that how we do it. Integrate on that side. So first this little long symbol got to be on each side to balance. Yeah, you can't just put only one without putting the other one. Okay, you have to put both. So the equation will not change. Yeah, if you put only this side, it won't be equating to the other side. So if you put the integration on this side, you have to do the integration operation on that side as well. Yeah, so that's why you see this too. Now we start to put the integration is happening, okay, from this unit to that unit. Yeah, since we're dealing with time, we put the time. Here we're dealing with velocity, so we put the velocity here. See how easy that is? And then we just plug the acceleration given one, yeah, into here. Yeah, the acceleration again with respect to time. Yeah, this is also with respect to time. Yeah, so if you put that in, you can be able to put this in. It doesn't change because it's still with the respective time. Yeah, so now integrate that, change cosine to sine. As you change, you've got to put this, right, multiplication factor to the denominator here. Yeah, numerator and denominator, meaning like just remember, put it down. Yeah, so anyway, so and if you differentiate, sorry, if you integrate dv, yes, you're gonna get v. The omega is nothing but, we call it constant. Yes, so therefore you can safely take it out. Anyway, so these are the rules for calculus. I'm just introducing you a little bit. You don't have to do calculation in my class, okay? It just, if you recognize the operation going backwards is integration, and integration, we do this, will not be asking you the detail of how to convert this to this, okay? But you can recognize, oh, this is that. Yeah, if you want to know what integration is in common word, I would say integration is just the opposite of differentiation, okay? Differentiation is a process that you calculate how fast something is moving, okay? So that's we call it differentiation. And it's going to give you the rate of change of a quantity, like in position or velocity. Yeah, so if you have like a position function st, then it's going to its derivative is going to velocity. Yeah, and you're going to get like ds by dt, remember? So that's going to give you the velocity, and we call that derivative. It's just giving you how position changes over time. Yeah, and that is differentiation. It's just a wording. It's the same thing. Yeah, how position changes to velocity. Yeah, and then velocity changes to acceleration. If you go forward direction, that's, we call it differentiating, meaning how fast something is changing. Yeah, if it gives you the rate of change of something, rate of change of position, give you velocity with differentiate. Rate of change of velocity give you acceleration with differentiated mathematically to get that value in mathematical operation. Okay, then when you go back, oh, I want to get velocity out of acceleration, then you've got to integrate. Yeah, so integration is the opposite of your differentiation, and it's a mathematical operation, and it's just a process of finding in common words a total accumulation of a quantity, okay, over time. You're finding the total accumulation of velocity over time from acceleration, okay? So if you know the velocity, integration is going to give you the position, okay? I'm just going to write it down here. Integration of velocity will give you position, okay? Showing you accumulation of quantity means it shows you the total distance traveled over time, okay? So if you integrate velocity, you're going to get the total accumulation of the total distance traveled over time, okay? Total accumulation of position is total distance traveled over time. So that's integration in meaning, okay, physical meaning. Yes, so sometimes like we know the mathematical operation, but we don't really know how to define that physically. Yeah, physically mean you're trying to find the total distance traveled. You're trying to find the total velocity out of acceleration. Yeah, here you're trying to find the velocity out of position, acceleration out of velocity, differentiate. If you want velocity, okay, total velocity out of acceleration, integrate this. okay, total distance traveled out of velocity, integrate velocity. You will get that, okay? Meaning like I want the total, like distance traveled value, then do operation integration of velocity mathematically, and you will get that value. And that is what we're doing here, yeah? All right, the next example is going to be 2.2-1. So here is you want, we forward, okay? So you want acceleration. So that's this guy right there. And you want it from position is given, yeah? So therefore, anyway, so this is your equation for, so you have to go derivative, meaning you have to differentiate in order for you to get acceleration out of position. And we have to do the velocity in between, yeah? So first you're going to get the velocity out of position, differentiate, first differentiation, and then second differentiation. So first you go velocity from position, differentiate it, you will get that, okay? And then you're going to use this, and then now you have to get the acceleration out of velocity, so differentiate that. All right, so two times differentiation. All right, so now the equation has changed to this. So when you differentiate, you got that. Okay, I'm not going to go into how it goes. That's your mathematics part. Okay, in my field, we use a Python or MATLAB, and we just put that, and then just tell the computer give me differentiation of this. Okay, 2 times, meaning differentiate 2 times, and you're going to get that. Okay, all right, pretty easy, yeah? So if you know Python, so by all means you can use it, but again, I'm not going to ask you to calculate here in this course. All right, the next one is a 2.2-1. So now we want to get acceleration, yes, and you have to get velocity from acceleration, so therefore you have to integrate acceleration. Acceleration is given with this equation we're going to use, yeah, because there's no time involved in it, yeah. You're given a straight acceleration with respect to the position function, yeah. So acceleration as a function of position and velocity as a function of position, so therefore we're going to use this equation without the time, yeah. So now we're going that way, so we are going to do integration on this side and then on this side. So that's what we're getting here, yeah. Of course, 0 to s, 0 to s, and then integrate that, yeah, and you're going to get this, which is, yeah. So after you put everything and plug it in, so that one will go into here, yeah. See that, yeah, is equal to this guy, yes. So and then you will have to integrate this into here. So 2 plus 1, yeah, is 3 divided by 3. Then here is 1, so there is 0, so v 0, okay. Before we go into v, I forgot 1. So here's a 1, so therefore you have another 1. And that is a s to the power 0, and then plus 1 divided by 1, you're going to get s. On this side, you have a v1. So therefore, at 1 to the power 1 is 2 divided by 2, you're going to get this, okay? So that's your integration. All right, the next one, I'm going to go quickly. This one is going from acceleration and then go to velocity, yeah. So you have to integrate. You look at the equation and you have a time factor, which is position and the velocity, so we're going to choose this integration going backwards, so therefore integrate both sides and you're going to get that, okay. Your dt is going to go that way, okay. And of course we're bringing this on this side because to make it easier for us to integrate, yeah, because of this equation, yes. And of course then you're going to put that into there and solve it, yeah. And of course at the end you're going to get this. Just go slowly, okay. um, I will not be asking you how to calculate. You only need to recognize a little bit, that's all, okay?